So very good day to everybody once again. This is machine learning, and in this class we discuss more about the gradient descent methods. What are the various methods in gradient, and what are the algorithm, what are the steps, what are the procedures related to this. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, let me thank God for giving me this golden opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. So in this class, we discuss about gradient descent algorithm. What are the actual function requirements? What are the examples of non-differential functions? And about convex and then non-convex functions. Then we discuss about quasi. Quasi means half. Okay. Semi. Okay. Quasi convex functions. Then we discuss about the saddle point in a bivariate function. Then we discuss about the 3D plot, about the gradient descent method steps, the implementation of the gradient descent algorithm with the steps tracking function. Then we discuss about the quadratic functions. Okay. And finally, we are going to end this class with the results for various learning rates. So I will be giving you independent work for you. Please complete them at your best available time. And at regular intervals, I will be giving you some short videos to discuss the knowledge in our topics. Right. So this is gradient descent algorithm. Generally, it is considered as the iterative first order optimization algorithm. Generally, to find out the local order minima or maybe maxima for a given function, you will be using this gradient descent algorithm. So normally in machine learning or maybe in deep learning, you will be using this gradient descent algorithm in order to compute the cost or maybe the loss function associated. Okay. So for example, in the linear regression technique, in order to go for step by step, in order to find the maximum or minima, you will be using this gradient descent algorithm. Okay. So normally you can use this for the machine learning or maybe deep learning applications as well. And normally in the real time applications, you can use for control engineering like robotics or maybe chemical sector even. And of course in the computer games that you are playing, online games, okay, maybe like PUBG or maybe Free Fire even for the step size, okay, you can use this gradient descent algorithm. And of course in mechanical engineering like mechanical automation or maybe manufacturing even, you can go with the gradient descent algorithm. Okay. So you can say that gradient descent algorithm, it is not suitable for all the functions. It is only used or maybe it can be apt for some functions only. But there are two functional requirements. One thing is that a function has to be differentiable. And the second thing is it has to be convex. Okay, so I'll discuss about what is differential and what is convex. Okay, so differentiable means it should have a derivative like d by dx or maybe d by dy. Okay, so not all functions will be meeting this criteria. So if it is differentiable means then gradient descent algorithm actually works. Okay, and next requirement is that the function has to be convex. So we have two functions, one is univariate function and then bivariate function. Maybe for a single variate or maybe univariate function, so the line segment which is connecting the two functions points lay on the curve, okay, or maybe above the curve. If it is there means then it is said to be convex. Normally you would have studied in the mathematics functions like the curves, okay, parabola, convex, concave, you would have studied. Okay, so if it meets this criteria means then you can find the local minima and not the global minima. So these are the examples of differentiable functions. For example, f of x is equal to x square. So in this case, if you try to differentiate df of x by dx, it is actually, what is differentiation of x square? 2x. Okay. And similarly, 3 sin x. Differentiation is, if you differentiate sin x, you get cos x or cosine x. Okay. So 3 cosine x. And similarly for this one, f of x is equal to x cube minus 5x. For this one, 3x square minus 5 multiplied by 1, it is 5. Okay. So for each of the curves we will be getting, it is differentiable, which means that gradient descent function is suitable. Okay. And there is jump discontinuity also for non-differentiable functions. So f of x is equal to x by modulus x, f of x is equal to root of x, okay, f of x is equal to 1 by x, okay. So this is considered as a jump discontinuity. For example, here the function acts and afterwards here the function acts. Here nothing, okay, it is no continuity over here, okay. And similarly for this one, okay, this one, okay, and similarly this one, infinite discontinuity. So these are nothing but the non-differentiable functions. So for example, if there are 2 points x1 and x2 on a function's curve, so you can characterize f of lambda x1 plus 1 minus lambda into x2 is less than or equal to lambda of this one, f of x1 plus 1 minus lambda, you take it outside, it is a constant, okay, multiply by f of x2. So here lambda is nothing but the point's location on the section line, and its value should be from 0 and then 1. 0 left point, 1 is the right point. So for example, if it is lies between 0 and 1 means it has to be 0.5 ARM. Okay. So which means that it's actually a location in the middle. Okay. So these are the two functions with the exemplary section lines. Okay. So this is said to be convex. Okay. And this one, if it's line, okay, which is connecting this one, it is said to be non-convex. Then you check if the univariate function is actually convex. Okay, so you can check whether the univariate function is convex. So what you do, you try to calculate the second order derivative and check if its value is greater than 0 or maybe bigger than 0. So d square of f of x by dx square is greater than 0. So this is the condition to check if the univariate function is actually convex. Okay, so we can investigate. For example, let us take a function f of x is equal to x square minus x plus 3. So differentiate 2 times. Okay, so first derivative if you can take 2x minus 1 plus 3, this differentiation of constant is equal to 0. Okay, so this becomes 2x minus 1, and if you differentiate once again this one, so d of f of x the whole square divided by dx square equal to 2 multiplied by 1, that's all, it is 2, and this differentiation would be equal to 0. Okay, so this is equal to 2. Okay, so in this case it is greater than 0. So in this case you can say that this univariate function is said to be convex. Okay. So it's also possible for using the quasi-convex functions with the gradient descent algorithm. So maybe you can call it as the saddle points even, or maybe minimum maximum points. Okay, so here we will take a quasi-convex function f of x is equal to x power 4 minus 4x cube plus 2. Okay, so maybe one time if you differentiate. Okay, so this becomes 4x cube minus 2 into this 3x power 3, you become 3x square. Okay, so this 3x square multiplied by 2, you get 6x square. Okay, then plus differentiation of constant is equal to 0, so nothing. Okay, so this one you can take what you can take outside, common terms you can take outside. Okay, so for example, like x square you can take outside, x square multiplied by 4x minus 6. Okay, so this is the one time differentiation of f of x. Okay, and we see that the first derivative is equal to 0. Okay, so maybe you can say like this one, x square 4x minus 6. Okay, so you can check whether it is equal to 0. Okay, and x is equal to 1.5. Okay, so that you try to simplify. Okay, so for example, you can check the second order derivative also. Okay, so this one, okay, x square 4x minus 6, you try to differentiate. So maybe once again it is 12x square plus 12x. So maybe you can take x commonly outside, so 12x multiplied by x minus 1. Okay, so maybe this one will be having a solution, it is actually x minus 0. So it is the solution would be x is equal to 0, and this one x minus 1 equal to 0. So the solution is equal to x is equal to 1. So there are two solutions, x is equal to 0 and x is equal to 1. So these are the two solutions. So the value of the expression is said to be 0 for x is equal to 0 and x is equal to 1. What and all I am teaching are nothing but mathematics. which you have already studied. So don't say you haven't studied this one. You should have studied. In your lower classes, you should have studied. So the locations are said to be like inflection point, which is nothing but the place where actually this curvature changes from the convex to the concave, or maybe concave to the convex. So we can conclude that for x is less than 0, the function is said to be convex. And maybe for x which lies between 0 to 1, the function is said to be concave. Or you can also say that the second derivative, the derivative should be less than 0. Okay. Or for example, maybe x greater than 1 also it is said to be convex. So you can say function is said to be convex when x is less than 0 or maybe x is greater than 0. And from 0 to 1 it will be concave, or maybe second derivative would be less than 0. Okay. So maybe we can see the point x is equal to 0 has both first derivative as well as second derivative which is equal to 0, which means that it has a saddle point. Okay. And the point x is equal to 1.5, what you found here. Okay, this one 1.5. Okay, so it is said to be the global minima or maybe global minimum. Okay, so maybe we'll look at the graph. Okay, so we can calculate the saddle point at x is equal to 0 and minimum at x is equal to 1.5. Okay, so this is actually 1.5. Okay, so this is the function. Okay, so from here you will get the saddle point from where it's actually meeting. This is the saddle point. Okay, 1.5. Okay, and this is the x is equal to 0. X is equal to 0, x is equal to 1.5. You will get the saddle point. Okay, so this is a semi-convex function with a saddle point. And then you'll have a saddle point in a bivariate function also, like the 3D plot. Okay, so for multivariate functions, the appropriate way is in order to go for the saddle point, we calculate for the Hessian matrix. So that will be a little more complex. Okay, so earlier method what we saw, it's actually simple. So that is for the function z is equal to x square minus y square. We establish a 3D coordinate system. Okay, where you try to maintain the saddle point. Okay. Then coming to this topic, gradient. Okay, so in the case of the univariate function, it is actually the first derivative, or maybe with the bir derivative at a selected point, and maybe in the case of multivariate function, it is a vector of the derivatives in every main direction, or maybe derivative across the variable axis. Okay, so since we are interested in the slope along one axis, we don't care about the other derivatives. Okay, so that is why you call it as the partial derivatives. Okay, so the gradient for the n dimensional function f of x at given point is given by del. You should call it as del. Okay, don't call it as delta. No, delta of del. If this triangle upside del f of p is equal to dou f by dou x1 of p up to like dou f by dou x2 of p, then dou f by dou x3 of p up to dou f by dou xn, nth order of p. Okay, so it goes. Okay, so this is the gradient function for a n dimensional function of f of x. This is the 3D plot. Okay, so better understand, we can do a hand calculation. This is the function f of x is equal to 0.5 x square plus y square. For this one, you will be getting the gradient descent function of this order. And then we'll have a steeper slope. Okay, so let us assume we are interested in this gradient. Dou f of x comma y by dou x is equal to x, and dou f of x comma y divided by dou y equal to 2y. Okay, so for this one, you can say like we saw for the x1, x2, x3, x4 up to xn. Okay, so maybe for del of f of x comma y, it is actually x and then 2y. Okay, and for example, del of f of 10 comma 10, it will be 10, and then 2 multiplied by 10, it is 20. 2 multiplied by 10, it is equal to 20. So which means that slope is 2 times steeper along the y axis. Okay, so that is what we conclude out of this function. And these are the steps in the gradient descent method. First of all, you have to choose the starting point, what you call to be initialization. Then you calculate the gradient at this point. Then you make a measured or maybe scale step at the opposite direction of the gradient. Okay, so you have to minimize. Then repeat these steps: initialization, gradient. Okay, you repeat until one of the criteria is met. For example, if you meet the maximum number of iterations, 1, 2, 3, 4, for example, maximum iteration you meet, or maybe the step size is smaller than the tolerance. Step size is meeting the scalability, or maybe the smaller gradient if it is meeting means, then you stop the method. So this is with the case of OpenCV platform. Import numpy as NP, define the gradient descent. Okay, start, gradient, learn rate, maximum iteration, and tolerance value equal to 0.01. Then the steps, you are going to have the start, the initialization point. Okay, then x is equal to start. For in range, you are specifying the maximum iteration. So differentiation equal to learning rate multiplied by gradient of x, and if NP numpy.apps absolute value of difference is less than the tolerance, then you try to break. Then you will go with x is equal to x minus difference. Then you append the statement history tracing. So steps dot append of x, and you return the steps comma x. So whenever we saw this one, the program, okay, so you will have like 5 parameters. One is starting point. So you have to go with a random initialization. Then you'll go with the gradient function. Okay. Then you'll go with the learning rate, nothing but the scalability factor you are measuring, okay, for the step sizes. Then you go for the maximum number of iterations. If you made the maximum number of iterations, then you stop. Okay. Or maybe if it is lesser than the tolerance also, you try to stop. So here the default value is actually 0.01. So this is the quadratic function. F of x is equal to x square minus 4x plus 1. Okay. So since it's a univariate function, we calculate first derivative. What is first derivative? 2x minus 4. This one differentiation of constant is equal to 0. Okay. So 2x minus 4. So here in the Python, you have to define the function 1 of x, return this. Okay. 2 multiplied by x minus, this function x square minus 4x plus 1, x star 2, okay, minus 4 multiplied by x plus 1. Then you go with define the gradient of the function 1 of x, which is nothing but return this function 2 multiplied by x minus 4. Okay. So you can repeat for the learning rate, maybe like 0.1, and maybe you can take the start point, initialization point at x is equal to 9, and maybe you can calculate each step. Okay. So for example, x1 is equal to 9 minus, you take it as 0.1. Okay. 2 multiplied by x minus 4. Okay. 2 multiplied by 9 minus 4. Okay. So what is this one? 9 minus 0.1 multiplied by, what is 2.9 minus 4? Minus 4. Minus 1.1. Yes, minus 1.1. Minus 1.1 multiplied by 0.1. 0.11, correct? 0.11. This one you can calculate. You can use the calculator, or maybe you can calculate on your own, and you can get the value x1. So this answer you are going to take. This 7.6 you are going to take once again. Minus 0.1. 2 multiplied by this 7.6 same, minus 4, 6.48. Again that you are going to take third function. Okay, 6.48 minus 0.1 multiplied by 2 multiplied by 6.48 minus 4. So that also will take. So 3 orders, 1, 2, 3, x1, x2, x3. Okay. So the Python function will be calling with this one history comma result equal to gradient descent. Okay, the function. The total, okay, the initialization point 9, comma, gradient function, it is 0.1, comma, the total which is actually 100. Okay. So these are the first steps which are taken by the gradient descent function for the smaller as well as for the larger learning rate. Okay. So for the learning rates 0.1 and 0.8, we will be categorizing the function. Okay. So it will be going step, like it will go through several steps for the smaller learning rate even. And when the algorithm is going to approach the minimum, the steps even, so when it is approaching the minimum, the steps are getting gradually smaller. Okay, like here it will be going like this. Okay, so for a bigger learning rate for this one, okay, you can jump from one side to another, okay, before converging. So for this one, it will go like this, and for this one, it will go ring ring. Okay, you can compare. You can compare. Okay, number of iterations and the final converge result. For example, 0.1 only like this. Okay, 0.3 also like this. But if it goes higher, 0.8 and 0.9 many. Okay, so this is the iterations 24, result is 2 point something, iterations 8, result is 2.0115, learning rate 0.8, iterations 15, result is 2 point something, and iterations 33, the result is 2.055. If you can see, this one is having more iterations, so that is the reason many zigzag. Okay, and comparatively this one, it has lesser iterations but it goes zigzag. Okay. This is the independent work for you. Multi-class logistic regression, ordinal logistic regression, and then plot calibration or maybe plot measurement. Please go through them. Please understand. Okay. Try to do with the case of topic, description, objectives, code, explanation. You try to understand that and attach the snapshot also. So I will be looking into the Google Classroom. Please submit them as soon as possible.